Okay, okay. Who do we have? All right. There's
Good
Gabriella.
morning.
Good morning with already the triple right there. And good morning, Jocelyn, with and both people being very early. I know. Thank you for waiting. And good morning, Sydney, and good morning, Nadine. Oh, we are rocking and rolling already. Um, and good morning, Effie. With even my 11-year-old son knows about Effie's. I don't know if anyway. Good morning, Melanie. Good morning, Sinead. Good morning, Mohammed. Good morning, me. Somehow, I hope you got. Oh, Mohammed, you were at the thing yesterday. Okay. Good morning. All right, we're going. Yes, I'm going to. Oh, and there's more people coming. And also, wait, I shouldn't get personal right now. Wait, who did I just? So good morning. I'm in the chat. I'm in the chat. Good morning, Melanie for the double. Good morning, Nadine for the triple, or Melanie for the triple. Good morning, Sinead for the double. Good morning, Lunar. Oh, where's Lunar? Okay, yes. Good morning, Lunar. Thank you. Good morning, Effie for the double. Good morning, Teresa. Good morning, Mohammed for the triple if you count me as part of that. Good morning, Sydney, for with the emphasis, with the enthusiasm, but where is Sydney? Oh, oh yeah, of course, for the triple, Sydney, yes. Um, good morning, Joshua. Good morning, Chanel. How do I see Chanel? But I don't. Oh, there's more. Sorry. Okay. Good morning, Jibo. Good morning, Angel for the double. Good morning, Christopher for the double triple for the triple G. Good morning, Genesis. Good mo and good morning. Where's Jen? Okay, and good morning, Norma. Awesome for the double. Thank you, guys. All right, and Gabriella, the Gabriella M is coming in. Okay. Let's. Okay, yes, let's get. So, I want to continue with. I'm. Tell me if I'm wrong. I'm assuming. I believe that you still your lab report like has not been turned in yet for lab 5. So I still want to say, and it's a huge lab. I mean, whatever. It's just it's a lab that's near and dear to me. I think it covers a lot of concepts. There's still things I want to say about it that hopefully will help you with your reports. But if you've already, let me know in the chat if I'm wrong. If you've already turned in your reports, I'll condense some of my comments. Um, but I think you have not. Right. Okay. But I also want to, well, okay. So we have not turned it. Thank you. Okay, I was actually counting on you to say that. Okay. Good. Thank you. And also, wait, not to get purse. What you have? Oh, and thank you, Angel. Okay, thank you both, Gabriella and Angel. Okay, so I'm going to continue talking about the lab. Um, yeah, someone's here. Wait, Joss. I thought Jocelyn was already here. Um, um. Yeah, so I've already gotten some feedback from some of you that suggests that maybe some of the things I was saying Monday about how and why we rotate the coordinate system and break up MG the way we do. Like it sounds like to at least maybe a couple of you that was maybe helpful, which is great. And it's good to get that feedback either way. Like I don't want to waste your time. So I'm glad if it was helpful for a couple of you. That also suggests to me, well, okay, yeah, no, I'm glad. But if you're still, the main thrust of Monday was why and how we break up MG the way we do. Um, and again, I want to emphasize, so I'm not going to repeat all that right now, but I do want to emphasize again, that's all strategy. Like, again, this is why, like, there's all this math in the class, but there's this Galileo principle idea. And it often, for a long time, seems to people like it's too, like, basically, it seems to a lot of people a lot of time that the Galileo principle stuff is kind of like a distracting waste of time. But the more you do physics, the more you see, hopefully, or the more I do physics, the more I see that Galileo's principle is like how we set up the math. I know I always say that, and here's an example. I'll say that is how we know how to set up the math. And an example here, just to reinforce, is that everything I'm saying now about breaking up MG, the reason for choosing to break up MG rather than breaking up diagonal vectors that seem like they should be broken up. The reason we break up MG and the way we break up MG, it's all a strategic choice. I just want to emphasize again, it's not a rule of physics that you have to do it that way. There's other ways this could be done. Breaking up MG may seem hard and weird to everybody at first, but the ultimate lesson is, and you're going to see, not today, but you're going to see other ways to do it that seem like they would be easier are actually harder. They're way more work. That's the surprise. So all of this is like strategic physics thinking. And I'm not making, I mean, it's common strategic physics thinking. Um, so if you do have any questions still about what we did Monday or about how to write your lab report, please, today's definitely the time. I'm looking at the chat. Okay, today's definitely the time. Um, but I'm going to, but today I really then want to, now I want to move on to like the friction part of all of this, like how the friction's playing in. And the punchline is right here on the board. You may already be familiar. I mean, that's the punchline, but I want to sort of show why. I mean, I want to explain it. Um, but first, a word from our sponsor. Well, here, oh, no, sorry. Let me do this a different way. Reset. A big punchline of Monday was this, right? That if the situation is a block on a plane where the plane is inclined at an angle theta as measured from the horizontal, then what we said, sorry, is if you rotate your coordinate system and line up the x-axis, the positive x-axis, with the expected direction of acceleration, which again is the big strategic pro tip for the rest of physics, to line up your positive x-axis with the positive direction of acceleration. Like that's what we're saying. Even when curves are involved, that's what we're saying. If we do that, then then this becomes the positive x-axis, and this becomes the y-axis, strictly the negative x-axis. Then the whole question was which one of those two components of gravity is sine and which one is cosine. And what we spent a while on Monday showing is I think that in that right triangle where we're breaking up the gravity vector, the angle that is down at the bottom of it is the same angle as the inclined plane angle as measured from the horizontal. Like, and if you believe that, if you believe that those two angles are the same, then it follows from SOHCAHTOA that this has to be mg sine theta and this has to be mg cosine theta, like opposite and adjacent. That's what we said Monday. But the whole key was really like, do I believe that that angle down there is the same thing as the horizontal angle? Well, here's another way to see that for the future, like how to choose which one is sine and which one is cosine, because that is always the issue in physics. Um, um, I'm going to ask you in the private chat really quickly right now. Question I'm going to ask, and I'll wait till I have at least three answers in the private chat, please, in the private chat. And anything you answer, you get points for, right? So here's my question: here's my question: what is the sign of zero? like the sine of 0 degrees in the private chat. Go, please. I'll say it again. What? So this is for everybody in the private chat. And if you can even say I don't know or I hear you, but I don't feel like answering, just say something in the private chat. Awesome. I already see, and I'm gonna say the question again. What is the sine of 0 degrees? And I'm looking at the chat. Awesome. I'm seeing a lot of answers, which is great. I'm not going to read out the answers yet, but I see. Wait. Oh, yeah. And somebody, at least one person, I'm literally asking for a number. Like it's a number. Like if you punched in 0 into your calculator and you hit sine, what would you get? And you could even try it if you want. But, and I'm, okay, I've got a ton of answers. Okay, I've got it. Oh, and some of them are not direct. Oh, no, they are all direct. Thank you for paying attention. Okay, and all of you should. Oh, well, one of them's not direct. Okay, all of you should submit for points for this, no matter what you said. Okay, I see a ton of answers in the. I'm going to just read them out loud. Obviously, some of them are public, which I didn't mean, but okay, I'm going to read them out loud. I hear one. I hear isn't sine y and cosine x. By the way, on that side note, great point. I mean, not exactly what I'm asking here, but side note. Actually, one lesson of I understand what you mean when you say isn't sine y and isn't cosine x. And when you're thinking in terms of the unit circle, that is a good way to think about them. And I love the unit circle. But actually, if you really want to, the farther and farther you go in math and physics, what's actually better is to think of sine, if anything, think of sine as opposite and cosine as adjacent. That will actually be more true for a longer period of time than the y. It's not actually always y and x like that. It is on the unit circle. But if you really want to like memorize, but anyway, all right, but going on, then I see one maybe, I see one, I see one, then I see 0, then I see 0, then I see 1. Oh, and that was the person who adjusted. Thank you for adjusting your answer. I get that. I see 0, I see 1, I see 0, I see 0, I see 0, I see 1, I see 1, I see 0, I see oopsie, that's okay. I see 1, I see, oh, I'll say it again because someone, I appreciate you're asking me to repeat. I'm asking what is the sine of 0? The sine of 0. I'm asking for a reason. Okay, and then I see 0, I see, I'm not sure, but maybe 0. Oh, it's 0. Okay. All right. So, folks, so good. Thank you for all participating. You should all submit for point. Yeah, and the unit. Look, I love the unit circle. Some of my best friends are the unit circle. I love the unit circle, and I'm not saying the unit circle is ever wrong. It's never wrong. It's always useful. Okay, but here's my point. The ant. I'm glad you all understand that the sine of 0 is like either 0 or 1, and then cosine's the other one, right? I think everybody's pretty clear on that, but it's easy to get them confused. That if you want an anchor for the rest of your life, if you want one thing to memorize to then base everything else off of, it is that the sine of 0 is in fact 0. I'm not saying that's obvious. I'm just saying it's true. The sine of 0 is 0. How could, and the cosine of 0 is 1. This is really useful for physics for the rest of your life. I'm going to link it back to this problem in a minute. It's like it helps you answer the question forever when you're resolving things into components, like which one is sine and which one is cosine. The sine of 0 is 0. How can you, and the cosine of 0 is 1. How, and yes, if you picture the unit circle, and if you know what one direct chat person said, that on the unit circle, like sine goes with y and cosine goes with x, like that's good. But let me even give you an easier way, since it is the anchor for everything. First of all, if you want to be like silly about it, like it's like all like sine of 0 is 0. Like think yourself as a snake or something. It's like all s's. Sine of 0 is 0. But better, honestly, I don't know if it's better. What I in my mind to this day, I always think is sine is super, cosine is counterintuitive. Or sine is super, cosine is crappy, whatever you want to say. Or sine is super, cosine is crazy. I mean, that's all silly, obviously. But what do I mean by that? I mean that sine does what you would want a function to do. If you had to make this stuff up on a desert island, you would make up sine, because sine of 0 is 0. And then as the angle gets bigger, the sine gets bigger, right? Picture the graph of it. It starts at the origin, like a nice everyday graph, like a nice simple graph would. Or sine is simple, cosine is counterintuitive, whatever you want. But sine is your friend. Sine is the one that starts at the origin and then it just goes up and to the right. Like when the angle gets big, as long as the angle is acute, as long as it's like, in the first quadrant. If the angle gets bigger, the sine gets bigger. Like how lovely. Like it's exactly what you would want, what I would want anyway. It's cosine that's crazy. Cosine already just starts at 1 when the angle is 0 and then starts coming down as the angle gets bigger, cosine gets smaller. Or cosine is confusing, whatever you want to say. Sine is the anchor to this whole thing. Cosine is the one that's like an adjustment on that. And again, if you can picture the unit circle, you do, and you picture the XY thing that one of you said in direct chat, then it all makes sense. I mean, it makes sense. But sine is the anchor. Okay. Sine of 0 is 0. If you want to memorize anything from trig, like to base everything, memorize that. Now, why am I saying all of this? What? Okay, but everybody's with me so far, right? I think just like, okay. I'm just going to assume you are. Why I'm saying that is if you go, okay, there's a strategy in physics. When you're trying to figure things out in physics, there's a strategy called limiting case. You look at the limiting case of a situation, which means you go to in your mind, you check an example that is so extreme that you would already know the answer for it. And if that's what you do. You check an example that is so extreme. So, in other words, if you're trying to make a math decision to fit the physics, you go to an example that's so extreme that you already would know the physics for it. So then you can see if you've picked the right math tool. What I mean is this. I mean, here's an example. And it usually involves the limiting case or the extreme example of an angle of 0. I'm saying we believe what we're saying now is if we have this, then if you have so no friction, assume for the moment, assume no friction. What we're getting at here is that if a block is on an inclined plane, let's say the simplest possible case, a block is like sliding down an inclined plane, no friction, no fanciness, right? We've decided to break up gravity into two components, one that goes along the plane, one that goes against the plane or into the plane. The whole question is which one of those is sine and which one is cosine. So look, so we guess. So what we do, I mean, I did this geometry yesterday, but it may or may not have worked for some of you. And it may be, in a different future physics problem, it might be different geometry. So what you do is you literally, one of these is sine and one's cosine, and we don't know which is which, but it's a coin toss. I mean, there's only two choices. So what we do is guess and check with limiting case. Like, um, we're going to make a guess and then check it with limiting case. I'll make the correct guess, right? Well, I'll do the correct guess so I don't confuse you or waste your time. Let's guess. If we guess that this one is mg sine. I mean, that is what I've been telling you. Like it is correct. But what would that mean? If this one's mg sine and this one's mg cosine, then what that means is that when the angle is 0, it means, sorry, if we say that, let me back up for a second. Gravity is pulling the block straight down. What we're saying is that in the case of an inclined plane, to pull the block straight down is to really do two jobs to the block. We're really gravity, the weight of the block, the actual natural weight of the block, is actually performing two functions. Some portion of that weight is shoving the block along the plane, and some portion, some fraction of that weight is shoving the block into the plane, keeping it like on the plane. That's two different jobs, right? We're asking ourselves which one of those jobs is it? And they're each a fraction, right? Sine is a fraction and cosine is a fraction. So we're really saying if this thing weighs 3 pounds, like some percentage of 3 is devoted to going like this, and some percentage of 3 is, or newtons, whatever, is devoted to keeping it on the plane. And the question is which percentage which? Sine is a percentage, cosine is a percentage. The question is which is which. So if we guess that it's the sine that's sending the block along the plane, then what we're saying is when the angle is 0, when the plane is horizontal, when it's literally just a lab table, then no portion of the weight is sending the block along the plane. And that's exactly correct, right? Like if the plane went like this, I mean, if you lowered it all the way down to make it horizontal with the lab table, there'd be no reason that the block should slide one way or the marble. I mean, the marble might be like jostly, but there's no particular reason. I mean, if you just put it there nicely, gently, why should it go to the left or to the right or to the left any more than to the right? It'll just stay there, right? But it will stay there. Like in other words, just that. If the angle were 0, the acceleration along the plane should be 0. So the vector that points along the plane should be the sine vector, because sine of 0 is 0. I'm really serious, right? And then even take it a step further, and then I'll stop. We'll take it 2 steps further. One is it's really logical. Like we're really saying if there's no friction, right? We're saying in this guess that mg sine theta should equal ma, like along the plane, along the x-axis of the plane, right? And therefore divide both sides by m. We're saying that a along the plane should be g sine theta if we guess that that factor is sine, right? Well, I'm here to say, oh gosh, that makes so much sense. Because if theta is 0, then a will be 0. And as the plane gets steeper and steeper, the A would get greater and greater. Like, duh. I don't mean duh like it's obvious, but duh like it makes sense, right? Like sine is super. Sine is the function we want to describe the acceleration along the plane, because sine gets bigger as the angle gets bigger. That's exactly physically what we all know. Even before we run a calculator on this, we all know here there should be no acceleration, and then as it gets steeper and steeper, there should be more and more acceleration until all the way it's like this, and then a equals g times the sine of 90, which means g times 1. Oh yeah, when it's purely vertical, the thing should fall down at 100% of 9.8. And anywhere in between, it's some percentage, some fraction that is bigger and bigger the bigger the angle is. Like sine is exactly the function that captures this. Now the only, and I will go, hopefully that, wait, so does that make sense? Anybody, does that make sense? Like, do you see what I'm saying? Nobody does. Wait, even with falsetto, you don't understand what I'm saying? Okay, wait. Okay, thank you, Lunar. Thank you, Lunar. Okay, you totally just got points for that. Oh, and I think is it a new moon today? Wait, speaking of, wait, sorry, hold on. I can't even resist. I think it's a new moon today. Or tomorrow. Oh no,
It's
tomorrow.
like 1 a.m.
Well, oh, she knows. Of course she knows. Okay, yeah. All right. So tomorrow. All right. Um, which means it's the beginning of the calendar month. And the new moon is known as Calends. Calends means to account. All right, anyway, whatever. Yes. Okay, very cool. Okay, so r- two quick more points on that. So look at the other side. Like if we had chosen cosine, that doesn't work because if we and even if you don't see the geometry, if we had said that this component is cosine, that would mean that at 0 degrees, the acceleration along the plane should be 9.8. Like what? Why would it accelerate at 9.8 horizontally? Right. And that would say that the steeper and steeper the plane gets, or the angle gets, the less and less this thing would accelerate. That doesn't make sense. Right. So what I'm really trying to argue to all of you guys is, again, this is a big thing in physics, is like which component is which. The real way to know is actually just to think about it physically. Just choose which one should be getting bigger and bigger as the angle gets bigger and bigger. Which one should be 0 when the angle is 0? And that one is sine, or like always for the rest of our life. So the angle, so the component that goes along the plane is mg sine theta. And then also, sidebar, this might actually start to get you to understand what sine, which I didn't. I never understood trigonometry or calculus until I started seeing them being applied in physics. Because, so sidebar, you might, well, here, I'll, so that you know this. Sometimes I put this on the final exam, actually, like, this is no friction. If friction is 0, so then I'll get back to the friction as per your lab. But just notice, if theta is 0, then the acceleration is 0. If theta is like 30 degrees, okay, very quickly in the chat, what's the sine of 30 degrees? And you probably
Do
have
you
two.
want it public or private?
Oh, private, please. I'm sorry. Yeah, let's just do private. So thank you. Private.
Corner.
What happened? So I'll repeat the question. Awesome. I just saw one answer that's also happens to be correct. What I want is the sine of 30 degrees. And it's like one thing or the other, right? So pick the smaller one of the two. If you know. Oh, interesting. I see many answers. Oh, okay. I see many answers. I think, okay, I see many answers, and many of them are right. Some of them are not. Okay. Nice. It's okay if you're rusty. Okay. I appreciate the honesty. Okay. Well, I'll read out the answers just so you also feel like, and I'm going to say again, I know I get so, I'm not doing this to test you guys. I'm not doing this to see what you know. I'm doing it to help. And well, I'll read the answers just so okay, because this is good for everybody to know. Like, I mean, do you need to know these things for physics? Like, ultimately, yes. But that's why we're learning physics now. It's not, the assumption is not that you came in knowing physics. The point is that we're learning. So it's okay. But yeah, what I hear in the chat. So I'm asking, the question is, what's the sine of 30 degrees, or what maybe next semester we would call pi over 6 radians. And what I'm getting in the chat is 1/2, question mark, rad 1 over 2, 1/3, 1/2, 1/2 with apology because it was a correction. I totally get it. 1/2, again, an apology, 0.5, which is the same thing as 1/2. I'm a bit rusty. Okay. Negative 0.988, which I'm going to say the negative 0.988, what that indicates to me is that someone's using a calculator, which is fine. I didn't say you couldn't, but I think your calculator might be in radian mode if you got that. Just saying. So be careful. So I'm asking of 30 degrees right now. Okay, and then I see 0.5, and rad of 1 is 1. That's true. Although rad of 2 is not 2, though. So a rad of 1. Oh, over 2. Oh, I see. I got you. Okay. And 1/2. Okay. So let me tell you all. I get this is not a quiz. This is we're I think the answer is one half. I'm going to say two things about this now. And again, this is physics. Okay, you need like this is physics, and this is relevant to the whole. And it's physics thinking. Like it's we math is the language of physics, but the content is physics. So we use the language, and it's more like conversational Spanish rather than literature Spanish, if you know what I mean. Like we're using math in a conversational way. Like I don't think a lot of physicists are not fluent in math the way mathematicians would want them to be. Like I don't know that they could necessarily like sway votes in the UN with a speech, but they could order a meal in a restaurant, if you know what I mean. Um, uh, I don't even know what I mean. But what I'm saying is, many of you probably remember somewhere in your mind that the sine of 30 is either one half or or radical 3 over 2, like right, but you just don't know which one is which. Now, what I've gotten used to in the years of physics is one half is 0.5, like one of you point out. And if you do out radical 3 over 2, well, radical 3 is like 1.7. And over 2 is like 0.866. I mean, it's like 0.17532. So what you start getting used to and what you kind of want to know after a while in physics is that radical 3 over 2 is like 0.866. What I'm trying to say is it's bigger than one half. So even if up until now you always kind of knew it was one or the other and didn't know which, what I'm trying to sort of drill in now is sine of 30 would be the smaller of those two values because 30 is smaller than 45 degrees. When you're in the small angles, you get small sines. Sine super, cosine counterintuitive. Like small, and you really will want to know this for physics 204, like small angles get small sines. Small angles get big cosines. So for what it's worth. So the sine of 30 degrees is one half. Where am I going with this? I'm saying, oh, and the other thing too is, again, I will shut up. But the way you learn the old stuff is by doing the new stuff. Don't be ashamed. And also don't tune out just because I'm talking about old stuff. I did not learn step A in my life until I had to apply it to step B. I learned college physics when I had to suffer through graduate school physics. Like, really? Like, college physics was for me to get exposed. I mean, I'm not saying don't learn this, but I'm saying it's always that way. You first get exposed to the thing that you're trying to learn and you get enough familiarity with it to like know what it is. But then it really starts to sink in when you use it in the next place. If you've ever felt that, you're not alone and you're not doing it wrong. That's how it works. So that's why here I spend a lot of time on the old stuff because I feel like here is where we actually can actually start seeing how the old stuff that you've seen before, but sort of just got yourself through, like it really, for me, comes alive here. I'm just saying. Okay, so you're okay. So example. If if theta is 30 degrees, then A will be G times sine of 30. Like this is all assuming A equals G sine of 30 is what I'm saying. If there's no friction on an inclined plane, A equals G sine 30, which really means it's some percentage of G that gets bigger and bigger as the angle gets bigger. Like that's what that means. And it totally makes sense to me. And but now look at a couple of like values. If theta is 0, then A is 0. If theta is 30, according to us, then A would be G over 2, like, say if like 4.9 meters per second squared. If theta is 45 degrees, then it's going to be radical. The sine of 45 degrees is radical 2 over 2, which I bet most of you did know because it's the same as the cosine of it. Like that's familiar, right? That's approximately here. Actually, let me make this even more consistent. I'm not changing, I'm just making like 0.5 of G. So 45 degrees would be about, if you do on a calculator, like, the square root of 2 is 1.414. So divide that by 2, you get like 0.707, right? I'll be super consistent. I'll be super consistent. And if you, right, and so these are all just percent. I'm rounding G. I'm rounding G to 10, just so you can see the pattern, right? And if you do 60 degrees, the cosine of 60 degrees is radical 3 over 2, which is like 0.866. So in other words, like 0.87 G, which equals like, so just look at this table for a second. I think this shows a lot of on the one I'm saying that table shows. So all I'm doing is plugging in G sine theta for the various thetas, right? And honestly, sometimes I put a table like this on the final exam. Like it's not a big deal, but or I ask you to complete it or something like that. Uh, on the one hand, I'm just showing the pattern that, oh yeah, if you pick sine as the angle goes up, the acceleration along the plane goes up, as you would expect, I think. And it goes up as some sort of fraction of the G value, the free fall value of 10 meters per second squared. And if we had picked cosine, this wouldn't work. The values would go down, not up. So this is why sine makes sense, right? Assuming the angle is measured from the horizontal. But now also just notice the angles don't go, I mean, the accelerations don't go up in direct proportionality. It's not linear. What you might notice is when the angle is a third of 90 degrees, you don't get a third of the acceleration value. When the angle goes up to half, like, 45 degrees, you don't get half of G. You get 70% of G. You see what I'm saying? When it goes up to two-thirds, you don't get 66%, you get 87%. The numbers don't go up as a straight line. Why? Because the angle is going up in a curve. Because this is what trigonometry is really all about. What we're really saying, this is what sine is. It's the function that applies to curves rather than straight lines. Like sine, this is y equals x, but this is y equals sine of x, if you know what I mean. Like the way these numbers are going up is the sine function, not the y equals x function. And because of what someone said before about the unit circle, when you go like this, you're not, when you go to half the angle, you're not at half the height, you're at half the angle. And gravity is just a vertical phenomenon. So what sine does is it extracts just the vertical aspect of this curve and spits it out to us. So the numbers go up in a curvy way, not in a straight line way. In other words, I'm going to move on now, but I will tell you the component that pushes the ball along the plane, the component of the weight is the sine component. If that makes sense, so in a way, arguably, I'm trying to show you what correct math to do for this physics. But on the other side, just for the record, when I saw this for the first time, obviously many, many years ago, but when I saw this for the first time, it was the first time I ever felt like I understood what the frick a sine function was in the first place. Like, and why it's like opposite over hypotenuse, or why it's the y component, the coordinate of the unit circle. Like, this is what sine is. It's the percentage of the acceleration that you experience as you're going down an inclined plane. Like the fact that those numbers are not going up one third, one half, two thirds that is what sine is all about. For what it's so I don't know if the math helps you with the physics or the physics helps you with the math. Either way, Quark bless America. Now I'm going to go on to add the friction now. Um, okay. What we said, so now I'm going to skip back to Monday. We added friction here. So the free body diagram for the up trip, I'm going to skip. cut to the chase, because we already did a lot of work on Monday. The component free body diagram for the up trip, what we said was, okay, we have mg sine going along the plane based on this whole analysis that we just did. We have mg cosine going into the plane. We have bad handwriting. We have the normal force like this, right? And then if we're going up, then friction is pushing us down. So we have friction like that. Now, and in the case of the lab, or in the case of this situation, this gets a little technical, but we're treating the object. I mean, the object is moving while all this is happening. It's already gotten going. So it's moving. So technically that's kinetic. So that would be kinetic friction because it's moving. Now, technically speaking, kinetic friction really means sliding. And all of this analysis is actually more accurate and better if the object that we had was actually like sliding along the ramp, but it's much easier to do the lab and to see what's going on with an object that's rolling. When it's rolling, there's technicalities involved that we are not stressing. But I'm just acknowledging, for the sake of the recording, that there are some subtleties because of the fact that it's rolling, but I'm ignoring those. I'm not ignoring them. I'm treating them as small compared to everything else. So this is my component free body diagram for the up trip, right? So the next step, if this were any kind of problem, now that we have a component free body diagram, that would be in a step method, the component free body diagram was step 4C, right? Like step 4A would be a system schema. Step 4B would be a pure free body diagram. Step 4C is the component free body diagram. So then what we do always, whenever we're analyzing any of these kind of force problems, step 4D would be apply Newton's second law along each axis independently, right? And so I'm going to do that now. I sort of did it very quickly on Monday, but I want to do it thoroughly now. This is what procedure for every Newton's law problem. You get your component diagram so that now every vector lies along either the x-axis or the y-axis or third axis. And so now you go one axis at a time applying F net equals ma, which is a vector equation. Pro tip, always, and I've said this before, but always save the acceleration axis for last. Like, we're ultimately interested in how this object accelerates along the x-axis, the axis that we deliberately lined up with acceleration. So we've set it up so that all the acceleration is along a particular axis that we're calling x. So I say always save that one for last, i.e. we're going to do the y-axis first. There's a number of reasons for this, to the y-axis first, one of which is, generally speaking, this axis will contain the normal force, which we're going to need for the other axis. That's one of the reasons for this strategy. So here we go. Tell me if you need me to go back. So we go to the y-axis first, and we apply F net equals ma to the y-axis, right? Again, it's a vector equation, F net equals ma. So it is true independently, yet simultaneously along every single axis. So we deal with one axis at a time, F net equals ma. So we look at the picture. In the picture, we have the normal force going in one direction, like along the y-axis, right? Here we go. That's the y-axis. The non-acceleration axis. So you got the normal force going in one direction, but then we have mg cosine theta going in a separate direction. So one of them gets a negative sign. We've tended to say that up on that, we've said that up is positive on that axis. It's not as, you can make either decision you want, but we've been saying that up is positive, right? Just like, but down is positive on the other axis. I hope that doesn't confuse people, but that is what we're saying. So I make this a minus sign. We're summing up all the forces. It's really n plus negative mg cosine theta, if you know what I'm saying. But so we say n minus mg cosine theta equals ma along the y-axis. Notice also, please, again, for the lab or whatever, like I know you've seen these equations, but notice how, like, it's not a memorizer. It's just the logic of that picture. If I did the picture right, and if I set up positive and negatives correctly, then it just follows from the picture. But notice, it all follows as long as from now, because someone asked me this like a week ago, G, lowercase g, I'm always just leaving as G. I'm never calling it negative G or negative 9.8 or anything. G is just G. The negative signs get applied to the whole forces by looking at the diagrams. So I have n minus mg cosine theta equals m a y. But now, right, that's a statement. But we know even though the lab never told us, no one ever told you, but you know that AY equals 0. You know, and that's important. It's really important. And it's not because of Newton's third law or anything like that. It is because the ball is not flying off the plane or breaking the plane, right? The ball is accelerating, but it's not accelerating along a line that's perpendicular to the plane. It's accelerating entirely along the plane, right? What I'm saying here is, in a way, we know that A sub y equals 0 because we chose the coordinate system to make that true. Like we lined up, this is why we're breaking up gravity. I mean, this is part of the reason. Because we decided to call x the line where the acceleration was occurring. Therefore, all the acceleration is along x. Therefore, none of the acceleration is along y. If we had not made that choice, and I'm going to show you this again in the next class, like what happens if you make the other choice. We could have made another choice that would still be correct and which would seem more logical at first. I mean, we could have just looked at the world this way. But if we looked at the world this way, then a ball that's going like this has acceleration along this axis and along that axis. We chose to rotate our x-axis so that we could get away with this belief that there is. Okay, I will go on. But again, why I get excited about things like this is because have no life. No, because what I'm really trying to emphasize always is it's looking more mathematical, right? Physics is looking, I think, maybe more and more mathematical. But what I'm really yelling about all the time is like the physics thinking is not in the computations. The physics thinking is in how we set up these computations. And the thinking was, let's go so that we're trying to make the computation. The other reason I get excited, I will move on, I promise. Paging Dr. Freud, paging Dr. Freud. No, the other reason is notice that these choices that I keep arguing that we're making, the choices are to make the computations easier, not harder. Physics looks like it's making everything so complicated. I'm here to tell you we're trying to make things simple. And not because I'm a teacher. But physicists are taking a world that is freaking complex and trying to make sense of it. We're not looking to make things more complex. It looks that way because the world is complex, but actually our version of it is simpler than the world itself. I promise you. And it's in fact the simplest version that we can come up with at any given moment. As complicated as this looks, this is what happens when we come up with the simplest version. I mean, behold the world. You see what I'm saying? All right, anyway, so we're trying to make it simple. So we want a to be 0 in that axis. Therefore, we chose this axis. Okay, so now we can say then, thus, like thus, in the y-axis, thus, so you get this, right? Now, I know a lot of you already knew that. I know that. Why am I? I don't know what that. How many cups? I think this is like a cup and a half of coffee. Like, can you imagine? All right, but a lot of you knew that. But again, I'm here to tell you because I've seen this happen before. That is, I know you know that. I know you used it in the lab. Blah, blah, blah. But please, if you're following me, if you're still here in the room, that is not a memorizer. That is not that is not a step 3, like ever. That is not a step 3. It's not a general definition or principle. It is a result for this particular situation because of like this whole analysis. The normal force balance, in other words, what that says in English, and I will move on. What that says in English is that in this situation, the support force from the track is, I'll put it in English. I'll write it. This statement right here, n equals mg cosine theta, which is not true in other problems. It's not a memorizer. Sometimes n doesn't equal anything. Sometimes n equals mg. Sometimes n does equal something, but it has nothing to do with mg. In this case, n equals, I mean, this case of the lab, 5, n equals mg cosine theta, which really means, I mean, this is the other function now. It makes so much sense to me, or it makes sense, I think, to you once you think it through. What we're saying is the track is supporting a portion of the weight of the ball. Some of the weight of the ball was driving it down the plane. Another portion of the weight of the ball is being supported by the track. However, this portion is the cosine portion. And it literally is a portion, like a fraction, right? Like a percentage, ranging from 0 to 1, right? But this fraction is the cosine fraction, meaning that if theta were 0, the track would entirely support the weight of the ball, right? Cosine of 0 is 1. So if the track were at 0, then the normal force up from the track would be entirely up and would fully support the weight of the ball. And all of the weight of the ball is supported by the track, and none of the weight of the ball would be sending it along the track. Then as the angle gets bigger and bigger, the cosine gets smaller and smaller. So as the track angle gets bigger, the track itself supports less and less of the weight of the ball, and more of the weight of the ball is sending it along the track, all the way to the point where if the angle were 90 degrees, the normal force is 0. It's a wall now, and the wall does not support the ball at all. The ball just free falls down. Right? You see what so I think it makes, again, to me, when I think of it this way, when I think of the sine as the acceleration along the track and the cosine as how much is being supported by the track, to me, that's the first time I've ever physically could picture sine and cosine. Honestly, like that to me is what brings sine and cosine alive. Just saying. But okay, but it's true either. But the real thing I'm saying, and I'm going to move on, and we still have 20 minutes, amazingly. I'm going to move on, but what I'm really trying to say here is that is not because of Newton's third law. Just saying. And this is often also on the, like, that is not, there's no law that says that just because you're pulled that way, you have to be pushed that way. No, then if that were a law, nothing would ever accelerate. It's not Newton's third law that are making these things opposite and equal. It's Newton's second law. It's the fact that the ball is not accelerating along that line at all. Okay, so we have that. So now That's the information that we got from the y-axis. That's why I went to the y-axis first, to learn about the normal force. Why do I care about the normal force? Because what I really care about is the acceleration along the x-axis, which involves friction, and friction depends on the normal force. So that's what, right? So now I go to the x-axis. So that's why I needed to do that. So now I go to the x. Now I go to the x-axis. So in the x-axis, okay, F net equals ma on the x-axis. So I look at my picture. It's all about the component free body diagram. All of this, it's all about the component free body diagram. But where did we get that? From the pure free body diagram. But where did we get that? From the system schema. Each one just has a set of rules. If you just follow the rules, you can't go wrong, but you got to believe the rules. You got to believe the rules, don't just accept them. Okay, so here's the diagram, right? So now I'm going to that to the x-axis. Notice in the x-axis, there ain't nothing balancing. We've got two arrows going in the same way, and nothing's on the other side balancing them. See, Newton's third law does not say that every arrow in a picture has to be balanced by some other arrow in the picture, despite what many websites will lead you, or many robots will lead you to believe. There's arrows there that don't have any balances at all. That's why the object is accelerating along that axis. The forces aren't balanced, so the A is not zero. So what do I put? And both of those arrows are going in the same direction. That direction is the direction of acceleration, which we called positive on purpose. So we say, okay, we got an mg sine theta going like that, plus a friction going in the same direction, so it's a plus. This is for the up trip. This is all up we're analyzing right now. Right. Okay. So all of that together equals ma along the x-axis, right? Again, this is what you did in lab. I'm just trying to explain it. And again, your lab report, you want to explain these things. Now, I'm not the one grading your lab report. I understand that. But often a problem like this does appear on the exam. You want to be able to explain this stuff, at least for me. Oh, and you have Professor Liu. Yes, she wants you to explain this stuff. And she will check for robots. I'm just saying. I think she hates robots more than I do. Okay, anyway, I love some of my best friends are robots. Okay. I don't know what that meant either. Okay, so we have this. So now we expand further. F always, and this could be a step. One thing that could be in a step 3 GDPs, it is true always, like we learned this on Monday or last Wednesday, like this is always true, right? The force of friction is the roughness coefficient times the normal force. In other words, why do we ever get this? Well, for two reasons. One, because we have this, and two, because we have roughness that's making this cause that, right? Because we're taking English muffins and putting them, or we're taking combs and squeezing them together, and the combs microscopically have grooves in them that get caught. So the more we go like this and the more groovy the grooves are, the harder it is to go like this. Those are the two factors, the roughness coefficient and the normal force between the two. So we plug in. We substitute. Like this is why we got this from why we bothered with the y-axis. Right, so now we have this 1024. Okay, so now we can divide both sides, but like we can factor out an m only because there's an m in every single term. We factor it out and then we can divide. You know what I'm saying? Like if there was not this m right here, we'd have a problem, but it's in every term. So we can factor it out. So we get that for the up trip, A equals G sine theta plus mu. I'm just abbreviating it to mu. There's only one kind of friction happening at a time here. So I'm saying this. Oop. Oh yeah. Yeah. Right. So that's the acceleration up is that. Like when the ball is traveling up, you have a contribution to its acceleration from gravity, and you also have a contribution to its acceleration from friction. And the friction and gravity are both working together. They're both working against the velocity of the ball, perhaps, and that's what makes this lab interesting. But they're both working together. Oh, okay. Here's now. I mean, we've got 13 minutes left. We're almost at the punchline. We're almost at the punchline. And again, I think you all know the punchline, but I think perhaps it's possible that the punchline is still. I think the punchline's a major surprise. Number one, I did not predict this lab correctly when I. That's actually kind of a lie because I made it up, but I wouldn't have. Um, um, and I was anyway. What I think you all know is that the ball takes less time. I mean, stop me if I'm wrong in the chat, but I think what you find, just regardless of your predictions, is that the ball takes less time to go up than it does to come down, which is not generally how we intuitively, expect the world to be, or certainly not me. I mean, the ball, right? I mean, just tell me in the chat or with a quick, I mean, we have 12 minutes left. Am I correct that you found that the ball takes less time to go up than it? Okay, thank you. Thank you, direct chat. Okay, awesome. Awesome. Okay. And am I crazy or is that's like slightly surprised? I mean, that's not what you I mean, I assume that's not what you predicted. Did you make a prediction at all? Let me just ask that. Did Professor Liu ask you to make a prediction before you did this? Yeah, okay, yeah, okay. And honestly, she did. Okay, awesome, awesome. And was that your prediction? I mean, be honest, because it certainly wouldn't have been mine. I mean, you're not dumb if you didn't. In fact, I no, okay, okay. They and she even went public with that. Okay, awesome. Right. Okay. So I think this is really interesting. As you could tell, I cannot fake this. I still think this is interesting that the darn thing goes whoop. By the way, literally, I mean, especially if you make the angle pretty, if you make the thing pretty unsteep and you flick it pretty hard, what's really weird is at the end of the day, when you do this, you don't even have to have stopwatches or rulers or anything. Like once you know what you're looking for, if you literally just do it, you can see with your eye. It's that vivid. And literally, if you ever babysit, I'm not trying to be weird, but if you ever, I mean, what my second son was like very small when I like sort of figured this out, and like I took him to the playground a lot. And like literally, if you take a child and you put him on a slide, I mean, a realistic slide that, of course, realistically has friction on it because it's like the real world. If you shove a kid up a slide, don't try this at home. Like you can see it with your eye. They go, whoop, like, I mean, it's not that exaggerated, but it's pretty exaggerated. So what the heck? Like, why? Well, the reason is that on the way up, what this diagram is showing is both of the forces are working together. They're working together to create an acceleration magnitude, to create a force, which is very high, and an acceleration magnitude, which is very high. And as opposed to, I'm going to do the down trip in a minute, on the down trip, they're in conflict. Gravity and friction are in conflict on the down trip. So it's subtraction, not addition. So you don't get as big a number, right? Like literally, if g sine theta is the number 5 and mu g cosine theta is the number 4, for example, then on the way up, you're getting 9 units of force slash acceleration or acceleration. You're getting 9 units, 5 plus 4. On the way down, you're getting 5 minus 4, 1. I mean, it's that simple in a way. It is that. And again, it's not that anything changed. The friction doesn't change. The gravity doesn't change. What changes is the relationship of friction to gravity. In a way, it's that simple that on the way up, gravity and friction are working together. So you get a huge net force and a huge acceleration. But if it's that simple, why would we all predict it wrong? Like if it's that simple, why didn't we see that from the first? Well, because what gravity and friction are doing on the way up is they're slowing the ball down, right? The reason everybody thinks it should take longer to go up is because you're thinking up. We always think up is slower than down, not because we're crazy, but because on the way up, you slow down. Your acceleration is in the opposite direction from your velocity. On the way up, you're losing speed. On the way down, you're gaining speed. So of course, it's natural to think that losing speed means low speed. And it's natural to think that gaining speed means high speed. The essence of physics is here to say that's the confusion we're trying to break apart. There's a difference between low speed and lowering speed. There's a difference between a first derivative and a second derivative. There's a difference between velocity and acceleration. And most of physics comes down to really seeing that distinction. The difference is that velocity is in the eye of the beholder, Galileo's principle, and acceleration is not. Let me say that in simpler terms. Well, I'll say it and then we've got 8 minutes. I'm saying on the way up, the ball is slowing down. Gravity and friction are working together to slow the ball down. On the way up, and I do encourage you, I don't use my exact words, but if anything I'm saying here is helping you in any way either understand how to write your lab report or literally how to write it, then Quark bless America. I mean, that's what I'm trying to do. I am trying to help you write your lab report. I mean, don't use my exact words. You can't read them anyway. But I mean, you can't read the handwriting anyway. But on the way up, friction and gravity are working together to produce a huge magnitude of acceleration, of net force, and therefore of acceleration, i.e., on the way up, the ball slows down at a high rate. It loses velocity on the way up very rapidly. And when does it get to the top? So it's losing velocity. So you think, well, that's bad. It's losing velocity. So it's like slowing down. So that can't be good. Like, why would that get it anywhere quickly? But think about it. Where's the top of the ramp? Where's it trying to get to? Where it's trying to get to is wherever it runs out of speed. Like there is no top. It doesn't get to the top of the ramp. It's not trying to get to a place. It will come back down once it's run out of speed. Goal up is v equals 0, right? So it finishes its up journey when it runs out of speed. So the faster it runs out of speed, the faster it finishes its up journey, right? Then on the way down, I'll just skip to on the way back down, as you know, the diagram looks like this. So the normal force mg cosine theta, that all stays the same. The y-axis stays the same, but the x-axis is that mg sine theta minus mu times mg cosine theta equals ma. Like now it's a minus sign, in other words. So the M's drop out. The M's drop out. So now on way back down, the ball gains back speed at a slower rate. And in fact, so slow, so it loses speed really quickly on the way up. Then on the way back down, it's gaining back its speed, but it gains it back at a slower rate. And on the way back down, what stops the ball? What ends the trip? The bottom of the ramp, as opposed to some particular speed. So it gets to the bottom of the ramp before it can gain back all of the speed that it started with. It never gains back. It never gains back all its initial speed. That's the key. Like, so if it's right, it loses speed until zero and then it gains back speed, but not so. If they say if it starts with 8 meters per second of speed, and then we have 3 minutes left, say it starts with 8 meters per second of speed, it loses until it gets to zero and then it starts coming back down. Now it's gaining back, but it doesn't gain back until a particular amount of speed. It gains back until it hits the bottom of the ramp, which is the same length up and down. So since it's gaining back at a lower rate than it was losing in the first place, by the time it completes that same distance again in the opposite direction, it hasn't had distance or time to gain back all of what it started with. So it would be like 8 meters per second, shoot to zero, and then to 6 or something like that. So the average speed, hence, on way up, the average speed on the way up is greater than on way. I wrote this badly. Yeah, well, on the way up, the average speed is greater than the average speed on the way down. The average speed on the way up must be greater than the average speed on the way down because it loses speed at a greater rate than it gains back the speed. And since the distances are the same, the time up must be less than the time down. In other words, we have 1 minute left. I mean, it is, to me, it is literally the difference between velocity and acceleration. On the way up, the thing is slowing down. On the way down, the thing is speeding up. But it is slowing down at a lesser rate than it is speeding up because of the forces switch. So therefore, on the way up, even though it's slowing down, its average speed is greater than on the way down. So it goes whoop, because gravity points in the same direction for both trips, but the friction flips. And that just flips one positive sign into a minus sign, and that makes all the difference in the whole thing. And it's 10:40. So you will get your exam. I will see you. Have a great next couple of days. Next week, I'll see you.
Thank you, Professor. Have
Thank
a good
you.
day.
Good day.
Thank you. Have a good
Thank
day.
you. Have a good day.
Take care, Professor.
Thank you. Awesome. Have a great. Thank you all. Bye. Awesome. And going what? Genesis, you're there. Going once. Going once. Going twice. All right. Thank you all. This has been a lovely, lovely discussion, monologue, soliloquy, therapy session.